The first speaker of our morning of our first session. So I keep saying it's morning session, but it's not morning for everyone, I understand. So will be Gavin Ramsay. So Dr. Gavin Ramsay from Armagh Observatory and Planetarium from Northern Ireland, United Kingdom. So Gavin will be talking about superflares on solar and low mass stars. This will be an overview talk for 30 minutes.
Perfect. Okay, so thank you very much for inviting me to give a kind of an overview of superflares from the sun, solar type stars, and low mass stars. So this image here, this is taken from the very north coast of Ireland, showing you that when it's clear, it's a perfect place to see activity from the sun. So I'm going to give a fairly low level kind of overview, just in case anyone's on this call who's new to the field. Maybe there's some summer students. I'm going to discuss what is solar activity, what are superflares. I'm going to then, again, fairly basic material, what's the difference between the sun and lower mass stars, how do we search for flares on other stars, how often do we expect the sun to emit superflares. I'm going to then go into stellar activity and exoplanets, and a very final slide on future missions. So we know that there's been evidence for solar activity for actually thousands of years. The Babylonians and the Chinese have records of Aurora. This woodcut here, which was made in 1570, this is an artist's impression showing a quite kind of amazing picture of an aurora. But as we move into the telescope age, on the right-hand side, this is Galileo was making observations of sunspot groups, and this shows a very large sunspot group traveling across the face of the sun, and he was able to determine that the rotation period of the sun on the equator was about 25 days. So I've shamelessly borrowed this from NASA, and this is going to, again, just remind us what the difference between solar flares and coronal mass ejections are. And you'll have to excuse the music. But one thing which solar astronomers have an advantage to stellar astronomers like me is they can show amazing images and videos of the sun. Okay, so we've now reminded ourselves what the difference between flares and CMEs are. So we might have seen kind of aurora on the Earth for millennia, and it's only in the last couple of decades that we've seen aurora on other planets in the solar system. This is Hubble images, quite famous images of Jupiter and Saturn showing aurora around the poles. This little footprint here, this is actually caused by unipolar induction, and this is kind of Io and Jupiter interacting. This is will be the subject of another topic entirely, but it's an interesting observation there. And so one other manifestation of solar activity, which has been known for several hundred years, is the solar cycle. when people, after Galileo, started counting the numbers of sunspots on a daily basis, they found that the numbers seemed to vary in a quasi-periodic modulation on around 11 years. This is now known as the solar cycle, and the magnetic flips once per solar cycle. So on the right-hand side here, this is kind of X-ray data taken by the Japanese satellite Yoko, and this shows that the kind of X-rays basically are from sunspot regions and coronal holes, but this shares the same quasi-periodic 11-year cycle. So we're now finding evidence for solar activity cycles on other stars. Obviously, this is much more difficult than the sun. And I just want to stress that actually making consistent observations of the same thing, as it were, over many years or centuries can give rise to very important kind of insight into whatever is being studied. So this is just a schematic of what causes solar flares. Now, people in this talk will know a lot more about this than I do. But essentially, it's magnetic fields from sunspots, which are starting to get wrapped around each other, and eventually they snap, causing either a flare and or a CME. So photons and or electrons and ions. So this whole workshop, I believe, is about superflares. So what are superflares? So this is two images which are in Hugh Hudson's review from last year, an excellent review, I've got to say, of the Carrington effect. So two English astronomers were making regular observations of the sun. This on the left-hand side shows one of these very large sunspots. And on the 1st of September, 1859, they both saw, I think, this region here, a white light flare, which I think they said it was as bright as Vega, which is a strange thing to say. But shortly afterwards, the new kind of magnetogram, which was installed at Kew Observatory in the west of London, this started to show intense activity. So the magnetic field was changing quite rapidly after this event. And then kind of 11 hours later, Aurora was seen in the Caribbean and other parts of the tropics. So the Carrington event is now thought to have an energy release of 4 × 10⁻32 ergs, and solar superflares are now regarded as being more energetic than 10⁻33. So what these events, like the Carrington event, do, they have kind of carbon-14 and beryllium-10, which can be absorbed by the atmosphere, which then goes into tree rings. And so on the left-hand side, this is a number of people have studied this, and they've found evidence from tree rings in the carbon-14 is that there's been at least 4 Carrington-like events in the last 7,000 or 8,000 years. So what was the impact of the Carrington event? This is a newspaper report from 1859. The telegraph wires useless for several hours, one of the most severe disturbances for many years, extending even to Europe. Telephone wires also obstructed, business delayed by a good part of the day. So some of you will remember that more recently in 1989, power was disrupted in Canada for 9 hours, and it caused extensive damage to various power station networks. So today, of course, we are much more susceptible to Carrington-like events. So potential damage to satellites. There's navigation issues from planes. There's also induced currents and undersea currents. So space weather events are now in the UK government risk register, and it's estimated that if there was a Carrington-like event today, it would cost tens of billions of dollars every day. So satellites have, in more recent years, the launch of many low Earth satellites. So when there's a solar event, it can basically heat up the Earth's atmosphere to a small degree, which causes drag on satellites. So in February of this year, 40 Starlink satellites were launched, and this coincided with a period of intense activity from the sun, and this caused the loss of 40 Starlink satellites and the cost of $50 million. So I'm now going to go to compare the sun with low mass stars. Now, I know that most people on this call will be aware of these differences, but sometimes it's good to be reminded. This is the HR diagram for stars within our galaxy. This was made by the Gaia satellite. So the sun's somewhere around about here. So the sun has an age of about 5 billion years. It's got a rotation period of about 25 days. So low mass stars, they are now starting to basically go down this part of the main sequence here. So we're defining low mass stars as lighter than 0.6 solar masses, and having a spectral type from M0 to late M type. So later stars are brown dwarfs. And again, it's sometimes good to remind ourselves that of all the stars in our galaxy, 3/4 are low mass stars. So how does the interior of these stars differ? Solar type stars have a radiative core and a convective envelope. More massive stars, this is reversed, and the core temperature is much hotter. But for low mass stars, after about later than about so M3 and M4, they are fully convective, and this influences how the magnetic field on these stars are generated and sustained. And it's just, again, nice to be reminded that the sun has a lifetime of 10 billion years. A star with a mass of 30 solar masses has a very short lifetime, 30 million years. But in contrast, for a star with a fifth of the mass of the sun, they essentially live forever. So the key point here is, can observations of other stars give us clues to how frequently superflares could occur on the sun? So this was work from Bradley Schaefer more than 20 years ago, and his group were looking at basically historical data. Some of it was from photography, kind of X-rays, even visual. I think that's great, and photometry. And they looked at 9 solar type stars. They weren't fast rotators, so they weren't predefined as being kind of more active than the sun. And they found 9 superflares with going up to 10 to the 38 ergs. And what they suggested from the study was that the sun hadn't had a superflare for the last 2,000 years. So I'm now going to go on to discuss how flares from stars other than the sun have been identified. So a big game changer was Kepler. So Kepler observed 115 square degree patch of sky just north of the galactic plane. And so unlike ground-based observations of stars, there's no data gaps because of daylight, there's no poor weather. And there was some interruption when data was downloaded. But for many stars, there were uninterrupted observations for 4 years. The main goal from Kepler was to detect exoplanets, and they were very successful in that. But they also provided light curves for accreting binaries, even supernova, pulsating stars, and what we're interested here is flare stars. So Kepler is been and gone. What is now observing, it's been observing for the last nearly 4 years. This is TESS. And so TESS is a very different kettle of fish than Kepler. It's observing what's called a sector, which is 24 by 96 degrees for 27 days, and then it moves on to the next sector. And then you will notice that the ecliptic poles, they're observed for 1 year. And so what happens once they've done all 13 sectors in one hemisphere, they flip back and they start doing the other kind of hemisphere. So it's getting very close to both hemispheres observed twice, and they will continue going, I think, in an extended survey. So this is the HR diagram of stars observed by Kepler. More than 110,000 stars had one brightness measurement every 30 minutes for nearly 4 years. And so just more than 5,000 had short cadence observations, so 1 point every 2 minutes for 4 years. Now, before Kepler, this was unimaginable that you could get light curves for extending so long and with very few gaps. But what you can see here is that stars of different temperature and mass were observed by Kepler. So this is the results from Shibayama 2013 on solar type stars. So here, flare energy is increasing here. This is 10 to the 38 here, and this is just the rate increasing up here. So this is solar maximum, solar minimum, and the stars down here, these are normal solar-like stars, and these are the most active solar type stars observed for the first year, I think it was, via Kepler. And the most active star, G star, has a superflare once every 10 days, extraordinary. And then, but on average, for solar type stars, it's one superflare 800 to 5,000 days. So this study suggested that the sun may have a 10 to the 34 erg flare once every 2,000 years. So the full sample taken from Okayama last year, they determined that for solar-like stars, you would get one flare with an energy greater than 7 times 10 to the 33 ergs every 3,000 years. So I mentioned that you could observe stars for up to a year with TESS. This is work led by Lauren Doyle, who's now a postdoc in Warwick. And this is a solar type star with a rotation period of about 2 days. Time is increasing along here and then increasing here. And what you can see here is that there's a period of intense flaring activity. And the interesting thing is that the rotation profile has now changed compared to when it was relatively flare inactive. And data like this and many other stars allows us to probe and question how the spot distribution and periods of intense flare activity, how they're related. And in this particular star, flares were seen up to an energy of 10 to the 36 ergs. So in TESS, this is from Tu et al. Last year. This again is energy increasing here. This is the duration of flares up here. Now these are solar events. These are solar type stars, and up here these are flares from a giant star. And so what they concluded was that the mechanism which is generating flares in the sun and solar type stars is the same. They would found evidence that flares saturated around about 10 to the 36 ergs, and possibly events greater than this may be caused by a different mechanism. So I'm now going to move on to activity from low mass stars. So this is observations from 1971. This is of UV-CT. This is 60 seconds here, a time. So this is high cadence observations. So it's interesting to note that TESS is now moving to a 20-second cadence for some stars, but this has second resolution. So this is UV-CT, which is the archetype of flare stars, and this shows kind of flares typically in the range up to 10 to the 32, 10 to the 33 ergs on a regular basis. Now, it's been observed for some time that flares are more common on later M-type dwarfs, M3, M4 and above, so they are fully convective, and flares with energies up to 10 to 35 ergs have been seen from these stars. So why is there a renewed interest in observing and studying M dwarfs? Well, it's largely to do with exoplanets. On the left-hand side, this is a schematic of an Earth-sized planet transiting a solar-type star, and this results in a relatively low transit depth. But in contrast, if an Earth-type planet transits an M dwarf, the contrast is much greater. So they're much easier to detect. And so we now know a whole bunch of M dwarfs which have got planets. In the case of Trappist 1, this is an active M8 star, and this has 7 exoplanets, and it's a very active star. And so one great kind of period of activity is groups looking to determine what is the effect of flares on the atmosphere of planets in stellar systems. So one way of studying this, the flares of flares from M dwarfs and indeed solar type stars, is to search for quasi periodic pulsations. Now, I think there's some presentations in later this afternoon on this, but this is work which we did last year. This is TESS observations. We observed about 10 or so red dwarfs. This is showing a QPP on 26 minutes. And what we were able to do is determine the loop length and the magnetic field in the corona of these flares. So this, again, is energy increasing here, and this is the duration of the flare. Again, solar flares are down here. The blue dots are solar type stars, and these red big circles, these are low mass M stars observed by TESS, where we've observed QPPs. And so the relative ratio of the loop length we compared to the radius of these low mass stars are much greater than the solar type stars. So this is a schematic.
Sorry, Gavin, sorry, you have 5 minutes left.
That's perfect, thank you. So this is a schematic which Lauren did of the loop length of these flares from these low mass stars compared to the habitable zone around these stars. So in some of these cases, the loops were extending a quarter of the way to the habitable zone. So the flares can affect the atmosphere of many planets in several ways. One is depleting ozone in the atmosphere. This is potentially bad for life. But alternatively, it's now thought that UV radiation from flares are actually essential to generate life from non-living matter. This is called abiogenesis. So we know that quite a few of these stars in our sample are going through the ozone depletion region, but there's several which were also going into the abiogenesis zone. I'm now going to very briefly discuss stellar activity and exoplanets. This is HARPS North data of the sun. So this is treating the sun as a star. This is the radial velocity here. Time is increasing along here. And the variation, which is a full amplitude of 10 meters per second. This is due to sunspot regions and active regions faculae coming into and out of the sun. Now, it's very useful to remind ourselves that the Earth has a full amplitude reflex motion on the sun of 20 centimeters a second. So there's a number of groups which are now looking to how can you start to get close to 20 centimeters a second in radial velocity studies. This shows one small 100 angstrom range of a solar type star, HARPS North. There are lots of lines, and if you were to take all the lines in that star, this is work from Dumsky et al. A few years ago now, you get an RMS of nearly 2 meters a second. However, if you were to take just lines which were known to be sensitive to stellar activity, you now double the RMS. Now, what you want to do is identify lines which are not sensitive to activity. And by doing that, they were able to get to 1.2 meters a second. So this is getting close to the 20 centimeters full amplitude that you need to get to detect an Earth-like planet going around a solar type star in the habitable zone. And we're now getting to about 40, 50 centimeters, which is getting tantalizingly close. I'm going to finish then with talking about future space missions. So Coronal, Kepler have been and gone. TESS, I think, is going to continue for hopefully many years. Cheops is another ESA mission. This is looking at single stars, so high precision transit observations. Plato, of which I'm the ESA community scientist, is going to be launched in the end of 2026, and this is going to be doing kind of observations of a very large field for at least 2 years to detect kind of Earth-like planets in the habitable zone of solar-type stars, and then kind of Ariel, which is due to be launched at the end of 2029. This is looking at the chemical properties of exoplanets. So just to summarize, I think the study of flares from the sun, solar-like stars, and low-mass stars can give insight to how flares are formed and how magnetic fields are generated and sustained in stars in general. I think it's important that we all remember the place of the sun in the context of other stars. I think governments, organizations, businesses should be prepared for space weather events. And I think understanding stellar activity is important for finding and characterizing planets and whether life could form on these systems. And I'll stop there.
Wonderful. Thank you very much, Gavin. So wonderful presentation as usual. And I think so this became an excellent introduction to the whole activity today. Thank you very much again. So we have a couple of questions and comments in the chat. So Ivan, do you want to begin and ask a question verbally? So please unmute yourself if you like and ask a question verbally.
Okay. Yes. Thank you very much for a very interesting talk. Yeah, I just would like to ask, can you comment a little bit how energetics of flares are estimated from other stars? And what is the precision of estimation, like dozens of percentages or one order of magnitude or something else?
Well, that's a very good question, and it does, and there's a lot of assumptions. So you need to know what the temperature of the flare is, and generally you don't know the answer to that. It's also likely that the temperature of flare events change during the course of the flare. So you have to make an informed guess. And then you need to know the real intrinsic luminosity of the star which you're observing. This has now been helped with Gaia enormously. And I think if you're getting, I think that the accuracy of the energy of flares is probably within the region of several tens of %, I would have guessed.
Yeah. Okay. Thank you.
Yep, and I would also add here that in addition to the need to know the temperature of the flare itself, you need to know the emission mechanism. So we should
absolutely, absolutely.
So
yeah.
It's another assumption we have here. All right, so I can see Wal's hand raised. So Wal, please go ahead.
Okay, can you hear me?
Yes. Yes.
Okay, Gavin, so thank you a lot. It was very interesting as usual. So just maybe rather comment, not a question, but say Kepler and TESS superflares are seen in the white light band. So while on the sun, we still debate what is the, say, physics of the white light emission. So hence possibly it's one of the, say, current challenges in the theory to link so the emission which we see in the white light, especially in superflares, so with other emissions which we are usually using to study solar flares like soft X-ray, hard X-ray, radio. So if you say a few words about this, and maybe a question is, you think so that the white light emission we see in superflares on stars is of the non-thermal nature or thermal nature? Like, oh, okay.
That's a very
crucial question for the estimation of the energy and everything.
Yeah, no, you're absolutely right. And to be honest, I can't remember. I'm sure there's people on this call who could answer that, but I'm afraid my memory is it's post-COVID kind of affected, I think. But you're absolutely right. But I think there's a cross-fertilization to be had here because it's much easier to determine what are the mechanisms from flares and CMEs on the sun. And if we can't really understand what's happening on the sun, what is really causing these flares, I think doing it from other stars may be trickier, but in some ways they could help solar physicists in trying to identify the nature for that. That's a bit of a hand-wavy kind of answer to your question, but I think this just demonstrates that there's a great mutual cross-fertilization which should be happening between stellar physicists and solar physicists.
Thank you.
Yes, thank you very much again. And possibly we have 2 last minutes for the very last short question, if someone have it.
Well, I'm just intrigued by Valerie's comment about possibly a superflare in 774 and 95.
Yep.
I'll have a look at that further. That's very interesting.
Okay. So in this case, let us thank Gavin for presentation and for question and answer session again.